This continues from our earlier video about building a virtual AI assistant that helps a human solve the New York Times connection puzzle. The AI assistant was developed using a specification-driven development approach, where an AI coding agent developed the software from a set of written specifications. If you're new to the idea, specification-driven development means that every part of the app, from the web user interface, backend services, and unit and integration tests to confirm correct operation starts from a clearly written specification. Instead of jumping straight into coding, you define what the system should do in plain language, and the AI coding agent uses that plain language specification to produce the software. Today's video will focus on what it's like to do specification-driven development using GitHub's Spec-Kit open source project. The focus here is on the experience, what worked well, what was unexpected, and the lessons learned from building the virtual AI assistant using Spec-Kit. In addition, I'll cover how the work was structured, a demo of the virtual assistant, and future work. For the viewer interested in how GitHub Spec-Kit works, I recommend the videos listed on the slide. Links to those videos will be in the description field. Let's get started. The work was split into two phases. In phase one, the focus was on building the foundation. I started by establishing the overall project structure, setting up the framework for how the front end and back end would interact. The web UI was built using React with TypeScript for the front end, giving us a responsive modern interface. On the back end, I implemented a set of Python services, just basically stub code at this stage, mainly used to simulate responses and allow testing of the front end. Finally, I put in place a testing framework to make sure each piece could be verified and extended in the second phase. Moving into phase two, the back end was significantly enhanced. This time, the stub logic was replaced to use generative AI large language models, or LLMs, to actually generate puzzle solutions. The key feature added was the ability to use multiple LLM providers such as OpenAI and Ollama, giving the user flexibility to choose a suitable LLM. And the web UI was updated as well, allowing users to select which LLM provider to use right from the interface. Together, these changes transformed the app from a prototype into a more capable, intelligent system. Link to the GitHub repo for the software developed in this video can be found in the description. Code generation was accomplished using VS Code in agent mode with GitHub Copilot. This table summarizes the Spec-Kit activities across phase 1 and phase 2, documenting how much time each step took to complete. Each row represents a specific activity in the specification-driven development row, such as defining specifications, generating test plan, implementing code, running tests. The LLM column identifies which large language model was used by GitHub Copilot for that activity, and the two time columns, phase 1 and phase 2, show the duration for each stage in minutes. In phase 1, the focus was on establishing the overall project structure and setting up the framework for how the front end and back end would interact. In phase 2, the emphasis shifted to building the phase 1 components and integrating with large language models from two different providers, OpenAI and Ollama. The row Code Fix-Up indicates the time I spent understanding the code and doing some code fix-up to make different components work together or correct an error made by the AI coding agent due to imprecise specifications. Altogether, completing both phases from initial setup through model integration and testing took about 14 hours of total work spread across several days of development and iteration. What you're seeing here is the delivered functionality from phase 1 and phase 2 of the project. On the left is the screenshot of the live interface of the virtual AI assistant. At the top, the UI shows the current status of the puzzle, how many correct groups found, and the mistakes made, and the puzzle words remaining to be connected. Next is the LLM provider selection area. As you can see in the interface, the user has the ability to select an LLM provider and the LLM model to use. This is followed by the virtual assistant's current recommendations for the word group and the connection reason. At the bottom, the assistant shows the history of the recommendations and whether they are correct or not. I'll now show using the virtual AI assistant in solving a connection puzzle. Okay, today we're going to do a live solve of the October 15th connections puzzle. So with this, again, ahead of time, I've typed in these words into a CSV file, which I'll now load up for the 15th. And then we'll set it up. And again, we'll just kind of confirm these words here have been properly written here. Okay, that looks right. All right. And again, for this, we'll use OpenAI because that seems the one to have the most power in solving these. So we'll do a GPT-5 mini, and then we'll get our first recommendation. And for this, it comes up with kidney, lima, navy, and pinto as types of beans. Right, so kidney, lima, navy, and pinto. Oh, that turns out to be wrong. Doesn't appear to be correct, so we'll just have to say this is incorrect. And we'll get the next recommendation. Alright, so now we have Bronco, Fiesta, Mustang, and Pinto as car models. Alright, so let's give this a try. Bronco, Fiesta, Mustang, and Pinto. Okay, well, I guess Pinto could have either been a bean or a car model. So let's see what this does. Oh, and that turns out to be correct. So at least we found the blue group. All right. So let's get the next one. And yeah, we have 1 out of 4 with 12 words remaining. All right. Bravo, Delta, Lima, Golf, Lima. All right. So this is the NATO phonetic alphabet. All right. So we'll give this a try. Bravo, Delta, Golf, Lima. All right. And that's correct. It's the NATO alphabet. All right. So in this we found the green group. All right. So we now have 2 out of 4 found with 1 mistake. All right. So let's now try the next one. All right. And here we have Elephant, Great, Infinity, Olympic. All right. Suggesting vastness or size. So we'll give this a shot. Elephant, Great, Infinity, Olympic. Nope, and this also turns out to be wrong. So let's, alright, so we'll mark this as incorrect. Alright, so now we have 2 out of 4 mistakes with 8 words remaining. So let's give this the next shot. Okay, pairs with CO. I'm not quite sure what that is, but we'll give this a try. Alright. So Elephant, great, navy, and vacuums. All right. All right. Elephants. Okay, that worked, and that's the purple group. All right. All right. Now there's only one last set of full words, and we'll now see if what the agent comes up with on the connection. All right. Types of pools. All right. It's a set of pools. All right. So let's do this. Yep. Types of pools. Okay. So we've solved it. Okay. So we'll say it's the yellow group. It's the yellow types of pools, and we've solved it. All right. So this was good. So for October 15th, our virtual assistant was able to help us solve it. Now let's put the capabilities built to a test. These results show the live performance of the virtual AI assistant solving the New York Times connection puzzle, where the virtual assistant is seeing the puzzle for the first time. No prior exposure, no pre-training on the answers. Looking at the data, you can see consistent performance across multiple days. The assistant successfully solved every puzzle from October 9th through October 18th. Even when the New York Times difficulty rating was level 5, the hardest category, the assistant still achieved correct solutions, often with zero mistakes. The New York Times solve rate column provides context. That's the percentage of human solvers who got the puzzle right. So, for example, when human solve rates drop below 60%, the assistant still completed the challenge successfully. These runs demonstrate the assistant can handle unseen puzzles in real time, showing adaptability, accuracy, and steady performance across varying difficulty levels. Let's now talk about what it was like working with an AI coding agent and doing specification-driven development with GitHub's Spec-Kit approach. Like any new development approach, using an AI coding assistant effectively takes time. This image illustrates the learning curve, the period where you're figuring out how to prompt, interpret results, and guide the AI to produce useful outcomes. At first, progress can feel slow. You're not just coding, you're learning how to collaborate with the AI. But as you gain experience, the curve levels off. You start to anticipate how the model responds, structure your prompts better, and refine your specifications more efficiently. That's when you reach the stage of effective use, where the AI becomes a real productivity partner rather than a curiosity. Getting to that point takes practice and patience. The image on the left captures what the workflow with an AI coding assistant feels like when it's working well. It's not about replacing the developer, it's about collaboration. The human brings context, judgment, and creativity. The AI brings speed, pattern recognition, and precision. You can think of it as pair programming session, where the AI handles repetitive or boilerplate work while you guide the direction, review its suggestions, and make higher level decisions. The key is staying engaged, asking the right questions, refining prompts, and stirring the conversation. Two of the best parts of working with the agent were, given my inexperienced web UI front-end development, the agent generated all the code for the front end. And on the back end, the agent did a great job increasing back-end test coverage from 55% to 80% in little over an hour. When that balance is right, the development becomes faster, more fluid, and a lot more enjoyable, like having a capable partner at the keyboard who never gets tired of iterating. This image represents a key principle when working with an AI coding assistant. It's not a fire and forget process. Just like launching a rocket, you don't simply press a button and walk away. You stay involved, monitor its trajectory, and make course corrections as needed. The AI can generate code quickly, but it still needs human oversight to ensure results align with the project goals, follow good design practices, and handle edge cases correctly. The example shown on the right would have been a disaster if I had just rubber stamped the agent's recommendation, because it would have deleted all the front-end unit tests. Think of the AI as the propulsion system. It provides speed and lift, but as the developer, you're the pilot with remote control, guiding it toward the right destination. That balance between automation and active guidance is what leads to consistent, high-quality outcomes. This was one of those points where progress slowed down. I had all the pieces in front of me, but they weren't fitting together the way I expected. Each component worked fine on its own, but integrating them exposed gaps and inconsistencies. Looking back, the root cause was pretty clear. The specifications weren't as precise as they needed to be. Some requirements were open to interpretation, and that ambiguity led to extra rework and confusion. It's a good reminder that even small, unclear details in a spec can ripple out and create big challenges later. The next few slides will illustrate this. This example shows how ambiguous wording in a specification can lead to unexpected results. I asked the agent to refactor the backend recommendation endpoint to use an LLM. What I meant was to modify the existing endpoint to call the LLM, but the agent interpreted it as creating a brand new version of the endpoint, leaving the old one in place. As a result, both the old and new versions of the code coexisted, along with duplicate Web UI components. The specification didn't explicitly say whether to replace or reuse the existing pieces, so the agent made a reasonable but incorrect assumption. If I had been more precise, I would have said something like, use the existing endpoint and refactor it to call the LLM. Do not create a new one. This small change could have prevented extra cleanup work later on. This is another good example of where specifications weren't quite specific enough. I told the agent to use LangChain with the required packages for OpenAI and Ollama, but it didn't explicitly say which modules. The agent defaulted to using langchain.llms, which is meant for legacy support. What I really needed was the newer langchain-OpenAI and langchain-Ollama modules. A similar issue came up with how the LLM response was handled. I said the LLM should return a JSON object, but didn't specify how. The AI coding agent produced code that returned a plain text string, which was then had to be converted into JSON. Instead, if I had specified using a chat API that supports the structured output method, like chat OpenAI or chat Ollama, the LLM could have returned a valid JSON object directly. It's a good reminder that precision matters, especially when dealing with evolving frameworks like LangChain and LLM APIs. This loop, plan, build, break, and fix, became my normal development rhythm. I use Git branches heavily during this process. Each experiment or prompt revision went into its own branch, which made it easy to isolate the changes. If the agent made a mistake, I could simply delete the branch and start fresh without worrying about breaking the main codebase. That flexibility was key. The agent is powerful, but it's not perfect. Treating each iteration as a branch kept things safe, clean, and easy to recover from when something went off the rails. One of the key design goals in this phase was flexibility. The ability to switch between a local LLM and a vendor-provided LLM with just a configuration change. This setup makes experimentation much easier. I can run quick tests locally using Ollama, then switch over to OpenAI or another cloud provider for larger scale validation. But for this to actually work seamlessly, both LLM providers need to conform to a common API schema, meaning the same input and output structure, the same request response format. Without that shared interface, every switch would require custom integration work. This approach creates a balance between cost, speed, and privacy, with local models handling rapid iteration and vendor models stepping in when more power is needed. Looking ahead, the key takeaway from this project is how I'll approach things differently next time. I'll invest more effort upfront in writing precise, testable specifications, the kind that remove ambiguity before any code is generated. One thing this project really drove home is just how literal the AI coding agent can be. If I say refactor the endpoint, it might create a brand new one instead. The agent does exactly what I asked, not what I meant. So going forward, I'll write prompts and specifications with that in mind. Explicit instructions, clear constraints, and no assumptions left unstated. Each phase taught valuable lessons, and those lessons are now shaping how I plan the next iteration. I want to pause here and highlight what you're seeing. This entire application was developed by a single developer, me. My background is primarily in Python and machine learning, with only limited web development experience and no real front-end expertise in TypeScript, React, or CSS. However, I've been working with AI coding agents for several months. Even with the gaps in my experience, using an AI coding assistant, I was able to plan, build, and deliver this working web application complete with a React front-end, Python backend, multiple LLM integrations using the best practice of a factory design pattern, unit and integration tests with 80% coverage, all code conforming to the project's coding style standards, including comments and function documentation. In roughly 14 hours spread over several days, with the assistance of an AI coding agent, delivered over 100 source code files with over 35,000 lines of source code. That's the real takeaway here. With the right workflow and clear iteration process, a single developer experienced in using AI coding agents can accomplish a lot. And that wraps up this phase of the project. This was more than just building an app. It was about learning how to work with an AI coding assistant effectively. The experience reinforced that success comes from iteration, precision, and continuous improvement. I'll carry these lessons into the future work, which includes some code rationalization and code cleanup to counter the effect of the earlier imprecise specifications, and continued enhancement of the application as a means to test GitHub's Spec-Kit in enhancing legacy application, where legacy in this context means an application with existing functionality that needs to be updated. Thank you for your time. If you've enjoyed this video, please like and subscribe to the channel. Thank you.